Okay, we are live. Audio and video is up. We're going to continue our discussion of RISA. What I'm going to do today is cover some of the things that we didn't quite have time to discuss in lecture on Wednesday about modeling. Maybe answer some lingering questions that I'm sure you might have about, well, how do you model an internal hinge, or how do you do this, or how do you do that? And then we will continue our sort of, I guess, full discussion by looking at deformations. One of the things I'll mention is, let me mention a couple logistical items, and we'll talk more about one of them on Monday. First off, for those of you that are operating Macs, I pulled the survey results that I had on Teams, and I've gotten virtual machines set up for all of you. You should have gotten an email from me to where you can access those machines at a distance and run RISA on your own. You're split up into groups because different faculty have reserved different computers for various classes. So the long and short of it is just make sure that you work with the folks in your group to ensure that you're not all trying to access the computer at the same time. The homework's due Monday. It's a pretty short homework. There's two problems on RISA, and basically I'm having you build those models and then query a bunch of results and put them in a sort of a Word or sort of a PDF report. And I'll show you what I mean by that here in a second. One other thing I did want to mention before we jump right into it is maybe starting to talk about our second exam. The second exam in here is going to be on deflections and influence lines. And if you look at the schedule, the class schedule, I have that exam to be like right before Thanksgiving break. And I'm happy to still do that, but considering the exams on deflections and influence lines, we're probably going to finish influence lines around, maybe like November 4th, something like that. And so I'm wondering if it's not worth it to maybe do that exam a tad earlier to ensure that all the material is fresh in your head. I'm not making that decision today. I'm just planting that seed for thought. Maybe we can talk about that on Monday. Let's get into it. Let's talk about RISA. Let's get back into the world. Yes, Mr. Atkins.
Just a quick side note on the next exam. Will there be a RISA-2D problem in there or not? Or it will take too long to do it with all the other
Short answer is no. I just use deflections and influence lines on the second exam. I may do a RISA problem on the final. I haven't totally made up my mind yet, but my initial thinking is no RISA on the exam. Let's get back to, let's start talking again about RISA modeling. So let's review what we did last time. So to build a model, we ultimately need to define two aspects of the model, the geometry and the loading. Today, we're going to add a third aspect to that, which is the stiffness, but we'll get to that. By geometry, I mean locating the points or the joints, assigning the boundary conditions or the reactions, and then defining all the members. By loading, I mean putting either joint loads or point loads on there, applying any distributed loads, and then building your load combos and running it. These are some things to watch out for when building a RISA model. The sign conventions for your applied loads, the downward loads are negative, so make sure that you're good on that. Don't forget to create your load combination. It's really easy to forget to build that final step where you do a load combination with basic load case 1 with a load factor of 1. And then your RISA sign convention for internal loads. The moment diagrams are going to be upside down, and compression is taken positive. So when you're querying the results, make sure you keep that in mind. Keyboard shortcuts. So F4 will delete a row in a spreadsheet. R is what you use to assign a reaction, and P is what you use to assign a append release. Okay, before I get into deflections, I want to talk about some additional modeling items, and I just have kind of like a slide on each of these. It's nothing we really need to spend a lot of time on, but it's just I kind of wanted to fill in some gaps. And so I want to talk about an internal hinge and a beam and a frame. I want to talk about roller supports that are inclined, and I want to talk about loads that are not vertical, that are at an orientation. So let's start off with modeling an internal hinge. So if you want to model an internal hinge in a beam, let's say you've got a structural model and you want to put a internal hinge at a particular point. For instance, like in our let's say we have an example here and we want to put a hinge like right there. because we're going to do this problem later. But let's say we want to put a hinge right there. What we would do is we'd put a joint at the point where we want to put a hinge. And then what we do is we go into the member advanced data tab. So remember, when you build members, there's the primary tab and the advanced tab. The advanced tab is what you use to release the ends of the members so that you're modeling a truss as opposed to a frame. All you do is, like, if this right here, if this is member 1 and this is member 2, what you do is you pin the end of member 1, on that right end. And that would create a hinge. Usually when I do it, I do both. But in fact, if you do one, that should work as well. Again, it goes from how you model a truss. Like when you're modeling a truss, all the members are pin connected, so you pin the ends of every member. And it's basically the same thing here, is you just place a pin on the end of the member where the hinge is going to be. And you can always tell that you've done that correctly, because if you look at your model, you'll see these little empty circles, like right here. I don't know if you can see that little empty circle. That empty circle indicates a moment release, and a moment release, that's a pin. That's a hinge. What about an inclined roller? RISA does not allow you to model a roller at an incline. You can't really do that, but you can get around it and still get the same answer. So let's take this problem here. This is a problem I believe we did in class, and there's a roller that's inclined at 20 degrees. What you do is you pull the same trick. You put a hinge right here at the end of this member, so you can see how those little white circles indicate that I put a hinge on either end. What you do is you draw sort of like a little short member that's at the same orientation as the reaction of the roller, and then put a hinge support right there. What you'll find is that if you compute I value, the degree of external indeterminacy, you'll find that both of these models have the same, they're both statically determinate, because you might have one more support reaction, but you also threw an internal hinge. So the beam on the bottom and the beam on the top have the same condition. As for modeling this little link, I'll call it a rigid link, what you do is you basically model with an infinite stiffness. So the idea, or to make the stiffness sufficiently high or sufficiently rigid, the idea is that as the stiffness goes up, the deflections go down. So if the stiffness was infinite, then that joint would experience no deflection, and a joint that experiences no deflection is basically a support condition. From a modeling perspective, when you apply, let's say, a boundary condition to joint A, so if you go to joint A and you say I need an X and Y reaction, one way of saying that is that when you have an X and Y reaction, you're saying that that point experiences no X and Y displacement. So those are one-to-one statements. They mean the same thing. So if you model this link as axially rigid so that it won't deform, it behaves the exact same way as a roller does that's inclined. So if you need to model an inclined roller, this is how you would do it. For the modeling techniques that we use, it actually doesn't matter how long it is. I just usually take it to be kind of short. And then if I want the reaction, just whatever the axial force in this member is, that's the reaction. In terms of modeling just a general load at an incline, RISA doesn't allow us to do that, but that doesn't really matter because I can take that and just model the X and Y components, and it's the same thing. So just use the slope ratio to compute the X and Y components and just model that. And so here you can see I've got this 20 kip load at a 3:4 slope ratio. I just modeled it as a 12 and 16 kip load. Notice the signs. The 12 is positive. The 16 is negative because it's to the right and down. And also notice that I've modeled these as point loads, not joint loads. Remember, joint loads go on the joints, point loads go on the members. And so that load's applied to the member. I just put 12 and 16 kips at that same point to the right and down. All right, before I start talking about deflections, any questions? I know I probably threw a lot at you. I just wanted to sort of fill in some of the gaps before we move on. And I know one of the things with the inclined roller is that, in order to model it, you have to model that link as sufficiently stiff, as has a high rigidity. We haven't talked about what that means, but that's actually what we're going to talk about now. Any questions before we get into deflections? All right, let's talk about deflections. So in order to model deflections, we have to introduce sort of the third aspect of our modeling. We have the geometry, we have the boundary conditions, we have the third aspect that we need to get right, and that's the stiffness. Okay, this word that I'm using, stiffness, is really going to be kind of a key term for us later on throughout the semester. But basically, if you want a simple definition, stiffness is sort of the ratio between the applied forces and the resulting displacements. So as a structure with a higher stiffness would result in lower displacements. In modeling, what does that mean for creating a structural model? It means ensuring that you've got the E value specified properly for your materials, the Young's modulus. I see your question. You said modulus needed? What? I mean, we will need the elastic.
You just said it. You just said the modulus. That's all I was. You already mentioned, yeah. So I thought that's what you're talking.
Yes, we'll need the elastic modulus for the material, and then we'll also need the cross-sectional properties. So we need like the A value, I values, so on and so forth. And that shouldn't be all that surprising. I think about, for instance, when we define or when we do truss deflections. How do you compute truss deflections? Well, you sum up these fractions, right? It's a little f, big F, L over what? EA. You need the E values and you need the A values for each member. So it makes sense that if we're going to get the deflections right, we need these E values and we need these cross-sectional properties. Now, there's a couple of ways of going about this. We're going to define our own, but I want you to be aware that RISA has a pretty wide library of commonly available materials already programmed into it. So, for instance, if you take steel design, one of the things you'll discover early on is that when you open the steel manual, there's oodles and oodles of different rolled sections. There's, W shapes, there's channels, there's angles, T shapes, you name it. All of those shapes are already pre-built into RISA. So when you're building a structure and this beam is W24 by 76, you just select W24 by 76 and all of the associated properties are already built in. Same thing with materials, all the steel grades, wood species, masonry, you name it. We're going to build our own, but I'll sort of run that by you. The way that the process works is, so in order to assign materials and section sets, what we're ultimately trying to do is affect the properties of the members. Okay, it doesn't affect the joints or the loads or the boundary conditions. It's all about the members. So the first thing that you need to do is you need to look at your materials. Now we can build our own material, which is what I've done here. You can see I've created this thing called Greg's alloy. So I went in here and I created Greg's alloy that has a Young's modulus or an elastic modulus of 25,000 KSI, and I left all the other properties 0 because I really don't care about them for the purposes of my analysis. So we'll say Greg's alloy has a Young's modulus of 25,000, and we create that. The next thing that we do is we create the shape of the member. So the idea is, let's say I'm looking at my rubber beam, here you can see on the camera. So what I'm trying to do is define the material, what this thing is made out of, and then I'm trying to define the shape. And what I mean by the shape is this. this is an I-beam, so I'm trying to define the numerical properties that define this I-beam. And so that might be its cross-sectional area, what's the area of this shape, the stiffness about the strong axis, and the stiffness about the weak axis. And I'll talk about what that means here in a bit. And so you can see here I've created a shape and I've called it Greg's shape. Okay, and notice how Greg's shape has whatever properties I define, but then I assign Greg's alloy to that shape. So I've said here's a shape and it's made out of this alloy. We'll call it Greg's alloy. And so now I've got Greg's shape. When I start drawing members, I need to go in and call them Greg's shape. And by calling them Greg's shape, you also assign that alloy property to that member. And so now that member has the material properties I want, and it has section properties that I want. That's it. That's really all there is to it, to defining materials and section sets. One thing that I want to make sure that everybody's clear on is the moments of inertia. So if you look here on the table, if you specifically look at this part, there's 2 columns for moments of inertia. And it might be a bit confusing, like why is there an I and it says 90, 270? Why is there one that says like 0, 180? Like, what's the deal? The deal is the different ways that you can bend a beam. So the way that I like to describe this is, if you're building, let's say, a deck outside your house, right? So here's the deck. You can see they've already dug their holes and cast their concrete piles, and they framed out the deck. Look at the joists here. See this joist. Notice how they oriented the joist so the long side is facing upwards. Now, before you started learning engineering, if you've ever done any type of carpentry or work on your house or whatnot, that's just the way that you do it. That just makes sense. But there's a reason why you do that. The reason why is if you compute the moment of inertia of this, rectangle, because that's a rectangular shape, what you find is that the moment of inertia when the beam is facing upwards is much higher than the moment of inertia when it's facing sort of horizontal. So this would be sort of, we'll call it its vertical orientation, and we'll call this its horizontal orientation. And so because the moment of inertia is higher, what it means is that beam is stiffer. It deflects less under the same amount of load. I mean, imagine if you had like a yardstick in your hand. The yardstick's really flimsy about that weak axis, and that's why we call it the weak axis. But if you try and bend it about its strong axis, it's pretty stiff. Okay, so RISA actually stores both of those quantities, and so it uses like the 90, 270 and the 0, 180. Think about like a coordinate system. So like 0 and 180 might refer to the x-axis, 90 and 270 might refer to the y-axis. According to common sign convention in RISA, the 0, 180 axis is the strong axis. So what we'll do is just, for 2D analysis, just use the 0, 180 column. In fact, if I'm being honest, for 2D analysis at 90 over 270, it really doesn't do very much for you from an analysis standpoint. This column here and this data here only really affects two things. It affects it if you're using these shapes for a 3D analysis, because the members could be experiencing all sorts of different effects. And the other way is in design. When you all take steel design, you'll find that the strength, let's say, let's just do steel design, for example, the strength of a rolled, let's say, rolled I shape in bending is a function of a number of things, not just its strong axis behavior, but its weak axis behavior too. So you'll need those numbers and those properties to compute its strength. It doesn't really affect the analysis, but it affects the design. And keep in mind, RISA does do design calculations as well. Okay. Any questions before we start just rocking and rolling and doing some problems? Okay. So I got two problems for you, and the first is a truss. If you remember, this truss is one that we did in class, right? And our method for computing the deflection was using the method of virtual work. So we did this truss and we analyzed it two different times. We analyzed it for the loads as they are, and we analyzed it with a single vertical load. I believe it was at joint C because we were finding the deflection at joint C. RISA, you don't have to worry about that. You just plug the structure in, hit go, and gives you the deflection. But in order to model it properly, you have to get the materials and the section sets correct. So let's think about our modeling approach before we start plugging and chugging. So we've got 4 joints, right? So A, B, C, and D. We've got 5 members, okay? Now let's take a look at the members, okay? Now here's the truss. How many different cross-sectional areas do we see, okay? We see, I got a 2 here, 2 here, 2 here, 2 here. But this one's 1.5. The diagonal's different. All the others are 1.5 or 2, but the diagonal is 1.5. And the entire truss is made out of the same material. So we can model this truss with one material, but with 2 section sets. Okay, so what I'm gonna, so what I'm gonna do is I'm gonna build this model like I did last time, pinning the joints. Those are gonna be joint loads, not point loads, applying our boundary conditions as appropriate, and chugging it out. So I'm gonna walk you through this one, and then maybe I'll give you a chance to do the next one on your own. So let me open up RISA. So maybe what I'll do, hold on, let's see if I can do some tiling here. Give me a second. Give me a sec. I'm going to close this, and maybe I can do something like that. Maybe I can put this here. That way you all can kind of see the truss and the model as I'm building it all at the same time. Okay, first thing we need to do is we need to build the materials. Okay, so here's the materials, and for this entire truss, we use one material, an E of 29,000 KSI. So here's the toolbar I'm using. I go into materials. And the first thing I want you to show you is that there is a lot of materials currently built inside RISA that are already there. These are all of the hot rolled steel grades. This is what we're going to be using in steel design quite a bit next semester. These are cold form grades. We won't really mess with that very much. Here's some wood species. We got Douglas fir and so on and so forth. Concrete properties. We've got masonry, aluminum, stainless steel, and then general. I'm going to use general. Notice here how rigid is defined. So if you needed to define a rigid link, you could use these properties. Just make that E value super, super large, and you won't get any deflections. I'm going to create my new material. We'll call it alloy. Okay. Now the problem states that E is 29,000 KSI, so 29,000, and we'll make everything else 0. You don't have to do that, but you can. I'm using the tab key, by the way. So if you're wondering, like, how is he going so fast? Oh, how is he going so fast? I'm just using the tab key to cycle through. Okay, and so I've got my alloy created, and I like to use the word alloy. I'm not a big fan of the word, but the word alloy doesn't really show up a lot in the native material property definition. So whenever I see the word alloy, it's like, oh, that's something I created. So I know it's the material I need. Okay, so there's the alloy, and it's already created. We can close that, and you can always reopen it, and you'll see it's still there. Okay, so then we move on and we go into section sets. Okay, now I want to show you a couple things. So there's hot rolled section sets, wood, concrete, so on and so forth. What you can do is, let's say you're using a hot rolled section set. You can go in and say, well, the default is a W10 by 33. No, I want something else. I can check that, and look, all the shapes are already built in. All the pre-built shapes, the W shapes, the channels, the angles, all that stuff is already there. You can even find Canadian shapes and Chilean shapes and Indian shapes. I mean, all these different standard sections are already here. What I'm going to do is I'm going to go into general, and I'm just going to make my own. I just wanted to show you that all that stuff is here. So we'll create our own shape. Now let's go back. How many different shapes do I need? Let me move this up here. How many different shapes do I need? Well, remember with this truss, I had all the members had an area of 2 square inches, except for the diagonal that had an area of 1.5 square inches. So if I'm naming these shapes, maybe what I'll do is I'll name it T2 and name it T1.5. I just made that up, T2 and T1.5. As for the member type, I'm going to leave that blank. The reason for the selection is so RISA knows how to do the design checks. We're not in a design class, so we don't need to worry about that. The material, we'll change that material to alloy, and then we'll change the area. So the area here is 2, and this area is 1.5. Now, one question I could always expect at this point is, some of you are like, well, Dr. Mike, I know what the areas are, but what about the I values? Well, here's the answer. I don't care what the I values are. The reason I don't care what the I values are is by pinning the ends of the members when I model a truss, there isn't going to be any moment. And if there's no moment, and there's no flexural bending, the I value isn't going to affect my analysis. I'm just going to leave those as whatever value they are. You can see it's like 1 million. It's not going to affect anything. Okay, let me close this spreadsheet. Okay, we haven't built any modeling yet. We've just done like some of the work in the background with the materials and the section sets. But everybody with me so far? Any conceptual questions before we keep on trucking? All right, and please don't hesitate to interrupt if you got any questions. Okay, I'm going to go now to start to define the joints. With this truss, I'm going to need 4 joints, so 1, 2, 3, 4. And turn my caps lock on. We'll call that A, B, C, and D. And as for the origin, I'll define A as the origin. So that's going to be 6 feet. That's going to be 6 feet. And that's going to be 8 and 8. So if I close this and maybe zoom in a little bit, there's my truss. You can see A, B, C, D. There's the 4 joints. Okay. Yes, sir.
If one of the supports had a moment reaction, would that mean that we would need I values for the entire truss?
You're talking about a fixed support?
Yes.
That's a great question. The short answer is yes, but keep in mind, trusses trusses by themselves. When you pin the ends of the member, they carry no moment. What I'm saying is that, well, here would be my point. If you modeled this truss and only put a single fixed support, by pinning the members, what you're going to find is that moment reaction is 0, and then you're only going to have 2 reactions. A truss with 2 reactions is unstable, and so the model won't run. Now, if you're modeling a beam, then yeah, you need the I values and all that, but that becomes a different story. Whenever you're modeling a truss, really fixed supports and rollers are all there is. You can model moment reactions, but they won't have any effect, and the moment reactions will be 0.
Okay, I think my question was that would probably make it would take it from a truss and then it would make it like a frame.
You're exactly right. And when you're modeling a frame, you need the I values and all that other stuff.
Okay,
you're exactly right. Boundary conditions, we've got 1, 2, 3, 4. And again, if you press enter, it's going to get upset because you can't define boundary conditions for joints that don't exist. Okay, so here's my truss. Oh, I've got something labeled incorrectly. Hold on. I need to look. You can see here. Look at my C and D, but I've got those backwards here. I need to flip those around. So maybe make this 6 and make this 0. I need to flip those around. Nobody caught me on that. Shame on you. I'm just messing around. Okay. So let's define our boundary conditions. Joint D. Joint D is a pinned reaction, so it's going to be R and R. So it's going to have a pinned support. What about support A? What's the reaction going to be at support A? Making sure you all are paying attention this Friday morning. There we go. Yeah. So X direction only. And so we just type the letter R. And again, I'm just using the arrow keys to go back and forth. Okay. So here's our truss. Now, in terms of defining the members, here's how I'm going to do it. The first thing I'm going to do is worrying about ensuring that the members are where they need to be. I'll assign the properties later. I'm going to need 5 members. So 1, 2, 3, 4, 5. Okay. So first off, let's just draw the members. So like the first one is member AB from joint A to joint B. Then we'll do the next horizontal. We'll call that CD, from C to D. Okay. Now let's do the verticals. Let's do AD. Oh, let's do AD from A to D. Let's do the next vertical, BC, from B to C, or to C. And finally, the diagonal BD from B to D. So before I start, assigning properties, let's get the truss looking the way it should look. Okay. Now, before I move away from the member tab, there's 2 things I got to do. The first thing I've got to do is assign my section. Okay. So if you remember, all of the horizontals and verticals have an area of 2. So if you look at this right here, they all have the horizontals and verticals have an area of 2, but the diagonal has an area of 1.5. And so what I'm going to do is I'm going to go into section sets, and let's test everybody's memory. If you go into section sets, remember what I named them. See how I named them like T2 and T1.5? So what I'll do is I'll just literally with my keyboard just type T2 down, T2 down, T2 down, T2, and T1.5. And so I'm using the name that I assigned here, and look what it did. Not only did it assign the section, but look at the material. It knew that the material needed to be the one that I created. So all of that's already built in. Now, the final thing that needs to be done before we go on is this is a truss. Okay, so because it's a truss, we go into the Advanced tab and use that letter P and pin the ends of all those members. Okay, and you'll know that you've done that right because you'll see those little circles that show that the members are pinned. Okay, now let's check this modeling out. I got 2 more things I need to do. I need to load it and I need to apply a load combination. We got 2 loads here that are applied at the joints. Okay. So before I do this, do you remember this button right here? I'll use my data entry toolbar to sort of point it. That button right there on the top left corner, this one right here, we need to turn that on so that when we create the loads that we'll actually see them. That's telling RISA to turn that visibility of the loads on. We're going to do joint loads. I got 2 joint loads I need to create, one at C and one at B. Let's do it alphabetically. Let's do the one at B first. That's a joint load at B in the Y direction, -80, going downwards. For joint C, in the X direction, and that's +60. There you go. Other than the load combination, which I'll go ahead and do that now, so don't forget the very end, load combinations, create a load combination and put 1 for a load case, a load factor of 1. You can do any one of those pairs. Now my model's done. Model is done, model is created, ready to analyze. I'm going to go ahead and analyze it. So remember, we could do the solve button or the equals button. We'll do the equals button, hit solve. Boom, we are done. You know you're done because you'll get another toolbar that pops up. Here's your joint reactions. Let's look at the joint deflections. What did we get when we did this problem in class? I think we did the vertical deflection and we got 0.401 inches when we did this problem in class. Exact same answer here. Pretty slick, you know, and keep in mind we got all the other answers that we also like. We got all the joint reactions. Here's the reactions. Here's the forces inside the members. Remember, we had some 0 force members in this truss. Pretty slick stuff. Let me show you a couple of things that I think are pretty slick. First off, I want to show you the model display options. So view, model display options. So again, this is the same stuff we did before. We can turn on all the reactions, and now we can see all the reactions that are there. If you want, you can look at the axial force diagrams. Kind of boring because they're just constant forces along all the members, and so you know you can see, okay, we've got 60 kips in tension, 60 kips in compression, 100 kips in tension. Again, it's kind of boring. But what I think is really the star of the show is the deflected shape. Okay, so what I'm going to do is I'm going to go into loads. I'm going to turn those loads off. I don't want to see those because I just want to see the structure. Now check this out. This is pretty cool. Let's go into deflection. Okay, now I want to show the deflected structure, and let's hit apply. And what it does is it does that. Now, first off, that looks probably a little wonky, but I want you to think about the numbers. Okay, this structure is what, like 8 foot tall, and it only experienced a deflection of 0.4 inches. What RISA is doing is it's magnifying those deflections so that you as the user can see them. It's using a magnification factor of 40. Okay, so maybe I'll tone that down a bit. Let's do a magnification factor of 20. Okay, maybe that's a little easier, a little more realistic. And if you hit this little check mark where it says include the undeflected shadow, now you can see what the truss looked like before and after. So this is before you apply the load, here's after you apply the load, and you can see how the truss forms. Notice at joint D, it didn't move at all. And at joint A, if it were to move, it would only move up and down. It wouldn't move left to right because of the reaction at A. If I want to get fancy, I can animate that. And you can see it's, it's going through that, start to finish. Just did 7, frames of animation. Any questions on this? That's a great question. Can you change the way the loads are plotted? If I'm being honest, not really. RISA sort of has like a standard way of plotting the loads, the boundary conditions, so on and so forth. Now, what you can do, let me turn the animation. Let me turn this off. Hold on. Turn the animation off. Now, one thing that you can do is you can turn some labels off. For instance, if you go up here, this little toolbar, I'll use the data entry. Like I'm talking about this toolbar right here, that right there. You can like turn off the node labels. You can turn off the boundary conditions. You can turn off the the labels on the members so that all you're seeing is just the truss. You can do that. You can't really change the direction of how things are applied. I know there are a couple things that you'd like to tweak, but such is life. Any other questions? Because I want to give you all a chance to model one of these on your own, and I'll build it with you near the end. All right, I'm going to pull up the slides. I want you to see if you can do this one. Okay, this is an overhanging beam. I want to determine the vertical deflection at B, the rotation at B, plot the deflected shape, so on and so forth. Now, let me say one thing. In order to model this structure, you do not need to place a joint at B. However, placing a joint at B does make it a little easier to determine the deflections at B because RISA automatically says, okay, here's the deflection. So I want to model this structure in RISA. We'll go ahead and place a joint at B. We only need one material, one section set, 4 joints. We have distributed loads. We have a joint load at 15 kips. I'm going to give you all a few minutes, and I want you to see if you can build this on your own. And I'll walk you through it near the end. If anybody has any questions while you're modeling it, please, don't hesitate. If you need me to blow something up or zoom into something, just let me know. I'm going to give you a few minutes on this. I'm going to close RISA. I'll reopen it and start from scratch. Maybe when somebody gets the model complete, like throw it in chat and say, hey, I've got an answer, or I'm getting stuck on something. Let me know. I'll give you all a few minutes.
Where does the I value come into play in RISA?
Are you talking about where to define it or where it comes into play? Like when you say where you define it. So you define it when you're defining your section sets. So remember how on this problem we defined a material with this parameter, and then we defined 2 section sets, and we defined the areas as 2 and 1.5. You're going to define one section set with an I value of 1,000.
Okay,
That'll be in your section
I values in the section set menu.
Yes.
So do I make
You
both
remember
of them
which
the
one to
same one?
use?
No.
Okay. That first off, for 2D analysis, if you're defining your own section, you can honestly just make them both 1,000. But the one that's going to affect your answer is the 0 to 180 column. But you could just define them both as 1,000 and it wouldn't affect your answer. and it wouldn't affect your answer because you're not deforming the beam out of the screen. Go back. Does that make sense?
Yeah, I think I'm following.
I'll give y'all about maybe 2 or 3 more minutes, and then I'll start building it, and we'll play around with it. For members, no, make a member for, so 3 different members, one from A to B, one from B to C, and one from C to D. I found that tends to reduce error, and there's another reason why I think you should get into that habit. What if, and I know it would make this beam, the particular beam on the slide, unstable, but what if I put a hinge at B? You know of any way to prevent? Actually, I think I might. Let me give me a second. I'm going to minimize this. I think if you right click and go to display settings, I think it's display settings. What you can do right here is see where it says change the text and a layout, or the layout of text. For instance, I'll mess around with it and see what it does. Oh my! So it's making, like, it's the same screen resolution, but it's making the text very, very large. So when I pull up RISA, oh man.
Yeah, that's how I ended up fixing that problem on my monitor. I didn't have it with that particular software, but a lot of software had that problem with scaling.
Yeah, that's I found in Windows 10 that's the easiest way to deal with it. All right, I'm going to go ahead and start building the model. So I'm going to move this. Let me see if I can actually, hold on. Give me a second. I'm going to close this. Put that over there. All right, I'm probably going to do this kind of quick, but that's the beauty of the recording, is that we can always, or you can always go back and review that. So first off, materials. We have one material and one section set that we need to define. So we go into materials. Here we go. We go into materials, go to general. We're going to define a single material. We'll call it alloy with a 29,000 and make everything else 0. I like to make everything else 0 because that sort of indirectly turns off shear deformation, so that when I'm checking like a homework or an exam problem, I get the exact answer by turning everything else to 0. All right, so that's my alloy. Section sets. Turn on the general tab. We'll make a single section set, and let's come up with a unique name. We'll call it Greg's beam. It is made out of the alloy. And as for the moment of inertia, if you're in doubt, just make them both 1,000. Really, the second one is the one that impacts your analysis, but you can make them both 1,000. It's not going to affect anything. Okay, materials and section sets done. Let's create some joints. So joints, we got 4 joints that we're going to create, A, B, C, D. Let's assume, here, let me drag this over here a little bit so we can see the beam. So we'll take A to be the origin, so 0, 0. We'll say this is 15, 0. Say this is 30, 0, and say this is 40, 0. And so there's my structure. Let's go into boundary conditions. So A has an X and Y boundary condition. C is going to have a Y. Done there. Members. Okay, 3 members. And we'll call them AB, BC, CD, A to B, BCD. Now, I need to change the section set here to Greg's beam, but I do not make the ends pinned. This is a beam. Beams and frames do not have pinned ends. They have fixed ends. So don't go into the advanced tab and release these. Just leave it as it originally is. Turn on my loads so I can display them. And then we've got 2 distributed loads, 1 joint load. So the joint load, let's do that first. That's on joint D. That's minus 15. You can see that there. The distributed loads. I got 2 of them, one on member AB, one on member BC. The start and end magnitudes are all minus 2, minus 2, minus 2, minus 2, minus 2. And by leaving the start and end locations blank, it default applies the loads everywhere, which is what we want on these members. Finally, on your load combinations, define a single load combination with a load factor of 1. Then we are ready to solve. Solve it out. Boom. Our joint reactions, deflections, all that stuff is done. Let's look at some results here because I think there's some pretty cool stuff to see. First off, we've got our joint deflections. Here you can see we've got joint deflections, and we also have rotations. The rotations are in radians. One of the things that's kind of deceptive but kind of interesting, look at the rotation at D. The rotation at D is 0. And that's actually really unique to this problem, and I'll show you why. Let me close this. I want to show you a couple of other things. So let's go to View, Model, Display Options. So we can show all of our reactions. Boom. There's here. Let me zoom outside. Get that out of the way. So here's our reactions. Boom. Let's see. Let's turn those off. Let's turn the loads off. Do I want to see the shear diagram? Boom. Turn the magnitudes on. Boom. There's your shear diagram. What about your moment diagram? Turn that on. Boom. Again, your moment diagram is going to be upside down, but that's okay. Now, what about deflections? Let's turn the moment diagram off. Go to deflection. We'll show the load comment or the deflection. Bam. And so what's happening is here's what the deflected shape looks like. And what's happening at point D is that it's actually going back to being flat. And so the fact that the result at D is 0 is really just I sort of designed this problem so that that would happen. If I change that load a little bit or change that joint location a little bit, that wouldn't happen. 2 things I want to show you before we call it. If you look on the very, very, very left of your screen, there's a little thing here called detail. If you see this little detail button right here, If you click that detail button, it sort of changes your cursor and makes it look a little weird. If you click on a particular member, it actually pulls out like a report where you can see, okay, that's what the shear diagram looks like on that member. That's what the moment diagram looks like on that member. That's what the deflected shape looks like on that member. So if you want to zoom in on a detailed report for a given member, you can do that. I mean, thing I do want to talk to you about before we close class today is something about your homework. Let me pull up your homework assignment. This is your homework assignment that's due Monday, and I actually made it worth 20 points, not 10, because it's like our one RISA assignment. So what you're going to do is you're going to take a truss and you're going to take a beam. So there's one truss, one beam, and I picked everybody's favorite beam. This is problem 735, the one that we just did, the one that had all those moment functions, because it's like the beam that you can't get away from. For the truss and for the beam, I want you to determine the vertical support or all the support reactions. I want you to determine the displacements and rotations of certain joints on the structure. For the truss, I want you to determine some internal axial forces. Make sure that you tell me whether or not they're experiencing tension or compression. And I want you to generate a plot of the deflected shape at a magnification scale of 20. Same thing, I want a deflected shape with a magnification scale of 20 for the beam. But I do want the shear diagram and the moment diagram for the beam as well. The moment diagram is going to be upside down. That's okay. And then the way that you're going to turn this in is I want sort of like basically like a single PDF with all this, so you could like build it in Word and just add it. This doesn't have to be like the neatest thing in the world. Like you don't have to write this like it's a master's thesis. But I do want it to be somewhat organized. For each problem, you should have a screen capture of the structure, which you could just use like your snipping tool in Windows or Apple or whatnot. I just need the screen capture of the structure. I want a summary of the data that you use to build the model. And so that could be screen captures of the data tables. That's fine. And I want all the forces, the deformations, all that stuff that the assignment's asking for. Just make sure you include a cover page. Submit that as a PDF. And you can also submit in Blackboard the RISA files, the R2D files. And so you can submit it all and submit that by Monday. Any questions? I had mentioned that earlier. Give me a sec. That was in the lecture notes. So if you're defining a member, this is why you don't draw a single member from like end to end, because if you need a hinge at a particular joint, you just go into the advanced tab and then release the ends of the member where the internal hinge is. So if you've got an internal hinge at node 2, release the member 1 at the right end and release member 2 at the left end. All right, any other questions? Because I know we're probably like a couple minutes over. Yeah, we're a couple minutes over, but any other quick questions? All right, next week we start probably the trippiest topic in this class. We start influence lines. With that, I'm going to go ahead and close it. You all have a wonderful weekend. Stay safe, stay healthy. We will see you all on Monday.